Never be afraid. There's nothing which is known which can't be understood. And there's nothing which is understood which can't be explained. For over 50 episodes now, my team and I have brought you to the very frontier of knowledge in physics and astronomy. And still, our mission goes on. To present you with your birthright, an understanding of the universe. I've traveled the world seeking out a certain type of genius. Masters of not only their academic disciplines, but also at explaining their research in understandable ways. And I've bestowed upon these women and men the title of Titanium Physicist. You're listening to the Titanium Physicist podcast, and I'm Ben Tippett. And now, allez, physique! One of the joys I have in my new job as a physics and math instructor at the College of the Rockies is to teach a course called Introduction to Astronomy. Oh, it's really neat. The class size is fairly small and the students are all first year. Most of them aren't planning on being astronomers or physicists. They're just, interested in astronomy. Oh, and once a week, there's a lab scheduled in the evening where you go up to the college rooftops with a bunch of telescopes and you learn to use them. Well, if it's not cloudy or raining or snowing, and this year it was only not cloudy twice. But the stars in the Rocky Mountains are big and bright, and you can see the Milky Way painted like a band of smoke from horizon to horizon. Anyway, in teaching the course, I reflected a lot on how much has changed since I was in my students' shoes. When I was 19, my astrophysics professor told us to get ready because the upcoming generation of telescopes were going to change everything. And he was right. Space-based X-ray and infrared telescopes and the refinement of huge adaptive optics telescopes on Earth mean that we can see space stuff with new and different and bigger eyes. And so, when I'm talking to my class of students, many ideas and explanations which I learned as conjecture or supposition have been confirmed and refined. It's almost heartbreaking how far we've come in the last 20 years. Because honestly, seeing so much further, seeing so much deeper, with so much more clarity, doesn't just come from a momentary stroke of genius. It requires new instruments and strategy and technology and leadership and coordination of huge teams. You need to build the cameras yourself, and you need to convince people to give you funding, and you need to convince other people to help you and collaborate for decades. My heart swells to see the work that has gone into these projects. But among these victories, there are a few which I never thought I would see. These are the really audacious projects, arrogant in their conceit and requiring technology which didn't exist at the outset, to see things that no one was even sure exists, requiring such precision and care and resources and coordination that I, a guy who can't even get the car radio on the correct radio frequency without help, thought it would never be done. I'm talking about the Higgs boson at CERN. I'm talking about the detection of black hole mergers a billion light years away with LIGO. And I'm talking about the direct imaging of a black hole by the Event Horizon Telescope. So many people needed to be right about so many things for these projects to work out that it really is a testament to their expertise, but also their carefulness and their ingenuity and their faith in one another. And all I can do from my humble seat in a humble town in the Rocky Mountains is applaud them and appreciate their hard work. Today on the Titanium Physicist podcast, we're talking about the Event Horizon Telescope and the first successful imaging of a black hole. Speaking of having to trust your collaborators, our guest today is an accomplished actor and improviser. Based out of Chicago and affiliated with the I.O. Theater, he's been performing and teaching improv since 2007. But if you don't live in Chicago, you've probably heard of him on the hit podcast Hello from the Magic Tavern, where he plays Chunt, the talking, shape-shifting king of the Badgers. And he also has a new podcast called Hey Riddle Riddle. If you want to hear these podcasts, follow a link from our website. Welcome today to our show, Adal Rifai.
Thank you so much for having me.
All right. So, Adal, understanding how a photo of a black hole was taken and then understanding exactly what they were taking a photo of is a fairly ambitious task. Luckily for us, two amazing titanium physicists have decided to help us today. Arise, Leo Stein. Dr. Stein got his PhD from the Massachusetts Institute of Technology and is currently an assistant professor at the University of Mississippi, where he's an expert in testing and exploring beyond Einstein's theory of gravity. And arise, Katie Bouman!
Caca!
Dr. Bouman is an expert on computational imaging. She got her PhD from the Massachusetts Institute of Technology, where she worked on the Event Horizon Telescope. She's currently an assistant professor at Caltech in the Department of Computing and Mathematical Sciences. All right, everyone, let's start talking about black holes. All right, Adal, did you hear the news? Is this a familiar thing when it came out?
I did. I saw the news appear on like my timeline, like Twitter timeline and stuff like that. So in passing, I flicked by it to see that there was some sort of blurry image taken. I did not read any of the articles about it. It did seem very exciting, but it seemed like, from what I could sort of discern, it seemed like it was a fairly young woman working with a telescope caught the image. Is that correct?
That's Dr. Katie Bouman. You're speaking to her.
Oh my gosh, you're the woman who got the photo?
Well, no, it was a big team. Many different people from around the world actually worked together to get it. It was just one little part of a big project.
So today, the ambitious project is to explain exactly what you flicked past in those articles. All right. So we've got lots of time. We can do this. It'll be fun. But we have to talk about what we were trying to look at. So what a black hole is, and the black hole specifically that we're looking at, we have to talk about kind of the basics of the instrument that they used. And then we have to talk about exactly how that instrument, the Event Horizon Telescope, put together all of that data. And it's a bonkers thing to talk about because it's a new aspect of astronomy that we've really gotten into in our modern age of supercomputers. It's fantastic. So let's start by talking about black holes. Do you know anything about black holes, Adal?
The extent of my knowledge of black holes is located entirely within the 3.5 minutes of the song Black Hole Sun by Soundgarden.
Okay, right. Yeah, so they wash away the rain, primarily?
Exactly. Okay, here's my idiot take on it. Black hole, big thing in space, pull stuff inside, suck inside, you go inside, you die?
Yeah.
Oh,
yeah,
you're pushing a lot of my buttons.
Yeah.
Oh, what? No, that's way better than Soundgarden explained it, honestly.
And also, I think we should change the Soundgarden's lyrics to Black Hole Shadow instead of Black Hole Sun.
That's true. That's true. So there's kind of one basic thing that you need to get to understand what a black hole is. And it has to do with Einstein's theory of gravity. So Einstein came around in turn of 1900s and wrote a bunch of papers, and everybody thought he was super famous and great. But one of his greatest accomplishments as a scientist was that he came up with a new explanation for how gravity works.
And this is the newest take since, like, Newton?
Yes, exactly. So Isaac Newton imagined that there were, like, invisible strings between the moon and the earth, or apples in your tree above your head, and these strings were pulling objects down towards the center of planets. So depending on how much mass your moon or your apple had, the planet would pull harder or softer, right? So a big heavy thing is heavy because the planet's pulling it in harder, right? Mm-hmm. Einstein had a different take that was kind of bonkers, and it's got a lot of attributes to it. You can spend years exploring all the ways that's different, but the basic idea here is that every object in the universe, and the universe itself, exists as something called space-time. Okay, so space-time is essentially a big four-dimensional sheet that everything lives on and in, and over time you kind of move forward in space-time like a little ant crawling around a table. So Einstein's picture said that gravity wasn't caused by forces, it was caused by curvature in space-time. And so the idea is the sun is sitting there right at the center of the solar system, and it's causing space-time to bend around it. It's kind of like, you ever see like a kid on a skateboard where they're just kind of riding a big curved skate park? The concrete in the skate park will be bent and curved, and the kid will be kind of going along a big, weird, curved path.
Yes.
So the trick to that is that they're not turning exactly. What they're doing is they're following the curvature. So it's not like when you turn the car where you have to turn the steering wheel. Instead, it's kind of like a NASCAR track where the curvature of the surface you're traveling over causes your path to bend. So the idea here is that it's not the sun pulling everything towards it. What it is it's the sun causing space-time to curve, and then the pull that we think we feel towards the center of the objects is just us interacting with the curvature. The curvature of the space-time is bending us towards things, which is fine. You don't need to worry too much about that, but the big takeaway here is that it's not that the object, the sun, is pulling us in. It's that the object is making curvature, and then the curvature is what's causing us to move in towards it.
Sometimes, like on the Discovery Channel and stuff, sometimes they have planets on this grid, and it kind of, like a rubber sheet kind of bending the space around it.
All we need to remember here is that it's not that the object is pulling us towards the middle, it's that the curvature is what's causing to pull us to the middle. The object's causing the curvature, and then the curvature is causing you to go towards the middle. Okay?
Gotcha.
So, what's a black hole? You know, earlier Katie Bouman said, you shouldn't call it a black hole sun, instead we should call it a black hole shadow. Mm-hmm. A black hole forms when an object gets so heavy that its structure can't resist the gravitational crush of its own mass. So the idea here is, if a star gets massive enough, there aren't any forces that are strong enough to keep it from resisting its own collapse, and it will collapse down to a point, okay? But the notable thing here is, when it does so, it leaves behind its gravitational curvature.
Okay.
So a black hole isn't an object, it's just a gravitational footprint of a star that collapsed to a point.
Yeah, this is something that's really funny about general relativity, that in Newtonian gravity, you need some stuff there. You need some, a table or a gas or some atoms or something to make a gravitational field. But in general relativity, it has this weird property that a gravitational field can itself create a gravitational field. So if you have a strong enough gravitational field, it can just exist on its own. And that's essentially what a black hole is. It's a gravitational field that's strong enough that you don't need any more matter there to create the gravitational field.
That's wild.
Yeah, nothing's there.
So black holes always used to be stars, is that correct?
The ones that we know about that are about, say, 10 times the mass of a typical star, or 30 or 50 times, those, as far as we know, they used to be stars that then died. And it's possible that some of those became black holes and some of them smashed into other black holes. And so that's how they got to be 60 or 100 times the mass of the sun. So those kinds of black holes, they just used to be stars. But there are other types of black holes out there in the universe called supermassive black holes that are like 1 million to 1 billion times the mass of the sun. And those were not enormous stars that collapsed. We think that they kind of grew up in mass as the galaxy that they're in was also getting bigger and bigger. And it's not really totally understood whether it's the black hole that's driving how the galaxy grows or whether it's the galaxy that's controlling how the black hole grows. But we see these supermassive black holes in the centers of most galaxies.
So if a star collides with another black hole, you said it will become a black hole?
So if two black holes collide, then they'll just become a bigger black hole. And if a star gets close enough to a black hole, then that black hole is going to rip it apart, and it might eat all of it, but it might just eat part of it and fling the rest out into space. And that can be seen. We call these things tidal disruption events.
Okay.
And so there are optical and infrared and radio observations of, just some spot in the sky that suddenly gets bright and then dim again. And based on the precise way in which the light gets bright and dark, people think that it's a star that's getting eaten by a black hole.
So if a black hole is made by a star collapsing under its own weight, what causes a star to gain weight?
Yeah, it's kind of like at the start of the day when you have lots of energy, but by the end of the day, you can't hold your own weight up anymore because you're too tired.
So like a 9 to 5?
Yeah, that's right. It just gets worn down.
Yeah.
Stars should collapse down to a point, but they don't because they're hot. The inside of the star has something called nuclear fusion in it. It's a nuclear process that releases energy. And so the insides of a star gets really, really, really hot, and the heat of it plumps up the star and keeps it from collapsing. But the deal with that is that it can run out of fuel. And so when a star gets really old, it burns through all of its fuel, and it no longer has that heat to keep it puffed up, and then it will start to collapse and might collapse down to a black hole. Sometimes it collapses down into a solid object, but if it's too heavy, the solidity of that object is too weak to resist the gravitational contraction, and it will keep collapsing down until it's a point. And then you just get a black hole because nothing's left.
So you can also think in terms of, in physics in high school, you might have calculated the escape velocity you need to, given some mass of an object, if you are on it. Well, you can calculate basically, how fast you have to shoot off of some massive object to escape it and go off to infinity. So you could say, okay, the escape velocity is related to the mass of the object that you're trying to escape from and the radius, how far you are from it. So you can also say, well, how big of an object does it have to be such that the escape velocity is faster than the speed of light? So if the escape velocity is so fast I could never escape it. For instance, for your mass, you can calculate the radius you need to compress it all down so that you couldn't ever escape its pull. So for basically any size object of some given mass, you can calculate the radius it needs to be, you need to smash it down to make it into a black hole. And so this can be done for any size object. So you could have these stellar mass black holes, these black holes that Leo was talking about that are only tens of size of the mass of our sun, but this can also happen for black holes that are billion times the mass of our sun.
Okay, let's break down what Katie just said, because this is a super important point to talking about the attributes of black holes. Because one attribute of a black hole called the event horizon is really crucial. The Event Horizon Telescope is named after it, and it's the reason why this photograph that you saw is just so breathtaking. And the idea is the event horizon is very, very, very small.
And so the event horizon is a physical descriptor of a black hole?
Yeah.
It's something you can visually see?
The event horizon is a place in space-time. So instead of saying that a black hole is a point, I prefer to think of a black hole as having a size, and that size comes from the event horizon. So it's like the boundary of no return. So if you cross the event horizon, then you can't come back out. So actually, if you were falling into a black hole and you had like a laser pointer with you, and right at the second that you're going through the event horizon, if you try to shoot the laser pointer back from where you were falling, then the light from that laser pointer is just going to live on the event horizon forever. So it's the place in space-time where photons that are going at the speed of light are moving out kind of at the same speed that space itself is falling into the black hole. So they're kind of trying to go upstream just as fast as the stream is going down, and they can't make any progress. That's what the event horizon is.
If you're at a party and you're having your fourth drink, it's the point of no return. Once I have this fourth drink, I'm committing myself to a night going up until the morning and
Yeah. Because once you're past there, you just keep drinking faster and faster and faster. Yeah. So let's together everything that we talked about, because it's understandable and it's important. So Katie introduced the idea of an escape velocity. And the idea here is, let's say Superman was at your house. What's the first thing you would ask Superman to do?
Wait outside while I clean up.
No, you would say,
my house is a mess.
Take this object and throw it straight up, and let's see how long it takes to fall, right? The same way you do if a major league pitcher showed up. You just like it when people go into your front yard and throw things straight up, right?
I mean, you and I have very different ideas of what we do with Superman, but that's fine.
So the idea here is, you've heard the old adage that what goes up must come down. That's not entirely true. If you throw something upwards fast enough, then it will have enough energy to escape the Earth's gravity, okay?
Okay.
So the idea is that there's kind of a threshold between not quite moving fast enough and will eventually fall back down, and moving so fast that it will never come back down. And that threshold is called the escape velocity. If you throw something upwards, faster than the escape velocity, it will escape. And if you throw it up slower than the escape velocity, it will not escape, and it will fall back down to Earth. So there's one big aspect to this, which is that the escape velocity doesn't just depend on how massive the planet you're standing on is. It also depends on how small the planet is, how wide it is. Like if you go up to the moon's orbit, the idea is that the Earth's gravity is much weaker the farther out in orbit you get from the Earth, right? You know that?
Correct. Yeah.
Right. So the idea here is that out by the moon, the Earth's escape velocity is lower than down here on Earth. Now, on Earth, that's as fast as the escape velocity goes for the Earth, because you can't go into the Earth, because the Earth is a solid object. But in these situations where you have like a black hole, the idea is that the surface of the star, in this case, can get as small as you need it to. And so it's possible for there to be things that are so small, but also heavy, that the gravity at that point is so strong that objects that are traveling at the speed of light won't be able to make it out. They're stuck on the planet.
Okay.
That's the introduction to the concept of an event horizon. The idea is that when you have a black hole, the object has collapsed to a point. So all that's left is kind of its gravitational footprint. And so when we describe black holes, we have to describe what they look like in terms of the gravity of the object instead of the characteristic. You know, if you have like a planet, you could be like, it's a red planet, or it's a green planet, or it's a wide planet, or it's a puffy planet. But when everything is collapsed down to a point, all that's left is the gravitational footprint, the space-time geometry that's left behind. And so when we talk about black holes, we're making reference specifically to the space-time geometry. And there's going to be a distance away from the middle where the escape velocity is essentially as faster than anything can move, the speed of light. And so the idea here is, if you're outside the event horizon, you're far enough away that the escape velocity is small enough that things can make it out to infinity. But at the event horizon, not even light can escape. And if you're inside the event horizon, then the pull towards the middle, the flow of space-time is so fast that not even light can emerge out. So it's the event horizon is kind of our descriptor of how big the black hole is, but it's also a descriptor of if you're outside of it, you're fine. If you're inside of it, you're going to get crushed to a point.
And that event horizon scales with how massive the black hole is. So a more massive black hole has a larger radius, so that if you're within that radius, you'll get crushed into the black hole. But a less massive, small black hole is going to have a smaller event horizon.
So when you talk about being sucked into a black hole, and you mentioned it should be called black hole shadow, is there an actual hole in terms of sucking something in? Is that correct?
If you want to use the terminology of a holes, the event horizon is like the lip of the hole, where if you're inside it, you're in the hole. And if you're past the event horizon, if you're farther away from the middle, then you are safe.
Just trying to wrap my brain around like what I've seen in movies. If you go into a black hole, it's not that you end up somewhere else, right? It's not like a tear in the fabric of space and time, right?
It's more like you're riding a river into a sinkhole. Actually, that's a pretty fun descriptor for it. It's like, imagine that we're in Antarctica and the glacier has melted. And so we're in a lake, fairly shallow lake, maybe in our kayaks, and that there's somebody pulled the plug on the lake. So it's all draining into this hole in the middle. Okay? Mm-hmm. The idea here is the closer you get to that hole, the faster the water is rushing and the harder it will be to escape. Mm-hmm. And so the event horizon is like the point of no return threshold around that hole. If you get too close to this, the water rushing into the hole is going too fast for you to kayak out.
Got it.
But you mentioned this shadow, and that is because of stuff that is around the black hole, actually. So black holes are cloaked by this event horizon where the extreme gravity is preventing even light from escaping them. But matter kind of more falls into the black hole than being sucked in. And as gas is like spinning around the black hole, it's actually superheated to hundreds of billions of degrees, so that before it passes through this boundary and we can't see it anymore, it actually shines very brightly. And so what we expected to see for many years was that we would see the dark shadow of a black hole on a backdrop of bright material. And so that is what we predicted we would see. And we called this the black hole shadow.
Yeah, that's a very important point that, if there wasn't any stuff around the black hole, if it was just a black hole sitting in space with nothing nearby it, then you wouldn't be able to see it. I mean, you might be able to see that something is there because of the way that it kind of lenses the stuff that's behind it. That's something that we could talk about, how it deflects light, but it doesn't emit any of its own light. It's not like a star. So there's no light coming out of the black hole. So otherwise, it would just be black.
Earlier, it was mentioned that you kind of have to describe a black hole by its footprint versus, saying the color or anything like that. Besides the size of it, is there a uniformity to what black holes look like in terms of like they look identical except for the size of the footprint?
Yeah, that's a really good question. And I mean, I think this is one of the beautiful things about general relativity, that all black holes in the universe, as far as we know, are just described by two numbers, just how massive they are, which is also how big they are, and how fast they're spinning. So just like planets and stars can spin, black holes can also spin. And so just those two numbers are enough to describe every black hole in the universe.
I will say at home when I'm watching the Olympics, that's how I describe figure skaters, is how big they are and how fast they're spinning. Those two numbers is,
This is called the no hair theorem, actually, where it's like there's no additional hairs, no additional terms you have to consider when thinking about how a black hole affects the space-time around it. Black holes are bald, as they say.
I really wish I knew the history of why it got called the no hair theorem. I think that there was probably somebody who was going bald that was working on black holes.
Oh, no.
like, if I'm going through it, so does space.
Yeah, that's right.
Just projecting onto it. Katie, what are the two numbers of the black hole you discovered? Like, is it possible to say it on the podcast, or the numbers so fantastically long that it wouldn't make sense to?
Yeah, no, that's a good question. So as Leo said, astrophysical black holes we believed would only be described by their mass and their spin if general relativity was correct. So this completely describes the size and the shape of them. The mass is the one that has the largest imprint. And so we see the shadow, the circular shadow, a ring of light. And the size of the ring scales with the mass of the black hole. And then the spin kind of changes the shape slightly, but it only changes it by about a 10% difference. So it's a much smaller imprint, I guess, on the shadow that we see. And so the black hole that we took a picture of, which is a black hole in the galaxy M87, which is about 55 million light years away from us, we think that it has a mass of about 6.5 billion solar masses, which is very, very big, very big black hole. But we're unsure of the spin of the black hole, although we believe it is spinning. But because the resolution of the telescope we use to get that picture, as you mentioned, we get a blurry picture, so we can't see that 10% difference with enough accuracy yet to say what the spin is.
Gotcha.
But hopefully in the future, we can improve our instrument, take more measurements over time, and learn more about it to try to nail that down too.
And just for clarification, this is the first picture ever of a black hole?
Yeah, so this is the first picture of what a black hole looks like on the scale of its event horizon. So again, we're not seeing the black hole itself, we're seeing the shadow of the black hole, but we've never seen anything at that kind of scale right up to the black hole's event horizon before. And Leo had said black holes are defined by the mass and the spin, but this is under the assumption that Einstein's theory of general relativity is correct. So one reason that we wanted to take a picture of a black hole, apart from it just being really neat to see the first picture of a black hole, is to see, does this theory hold at the extreme boundary where it is most likely to break down around a black hole, where you have this super small thing with extreme gravity. And so although we can't say that our picture prove general relativity is correct, it at least is consistent with the theory. So that was pretty exciting to see.
That's very exciting. I have to ask, do you have like a framed copy of this picture at home, like on a desk, above a couch?
Not yet, but maybe sometime soon. Yeah.
A picture of you in the black hole on a roller coaster, like Space Mountain or something.
You got to make t-shirts.
Yeah.
Katie, if I was involved in the first picture of a black hole, it would be a tattoo, probably a couple tattoos like on my neck. And
I did get for all our friends removable tattoos that we put on the night of the announcement, so it was fun.
That's wonderful.
M87 tattoos.
But it would be my Christmas card. It would be a tattoo. It would be in every room of my house. It would, instead of saying hello, I'd be like a black hole. Like that's how I would not let it, just like a black hole. Nobody would ever escape the fact that I took that picture.
Yeah, we were so excited to be able to finally tell everyone about it, because actually we made this picture a while ago, and so we haven't been able to print any pictures of it so far because we were trying to keep our mouths closed. We didn't want it to leak ahead of the announcement. So soon I'm sure we'll all get it printed up.
In the Milky Way, are there any black holes that we know of? Or is it just, like you said, if we can't see it or detect them, we might stumble upon it one day? Or are we certain there are or not?
That's okay. Yeah. So that's a good question because it's got a couple answers. One of them is that there's different types of black holes. There's supermassive black holes, like the one the Event Horizon Telescope took a photo of, in the center of our galaxy. There is one. But there are also ones that are about the mass of the sun floating around in space, in orbit, or in the galaxy along with us.
Wait, they can... This is news to me. They can move around?
Well, yeah. I mean, stars move around the galaxy.
Yeah, I thought for whatever reason in my head, in my mind's eye, they were like stationary and pulled things towards them.
Yeah, this is something that pushed my buttons when people say that black holes are like cosmic vacuum cleaners or they suck. But really, when you're far away from a black hole, they act really, really similar to just anything else of that same mass. So you can have a black hole and an ordinary star just orbiting each other, like two stars orbit each other. And that was actually the first like concrete piece of evidence back in 1963 or 4. We saw, we none of us were born then, but astronomers saw X-rays coming from this object that's called Cygnus X1. That's a kind of ordinary star that's in orbit with a black hole that's like 10 or 15 times the mass of the sun. That's actually eating a bunch of the gas from the ordinary star. And that's why we can see it, because all of that gas that's falling onto the black hole is getting really, really hot and emitting X-rays.
Wow.
So, to answer your question about whether or not we can see one coming, that answer has to do with whether or not there's any gas around it, in orbit around it. Okay?
Gotcha.
So if there was a black hole orbiting the Milky Way that decided to pass through our solar system, we could only see it coming if it passed between another star and us. And we somehow caught that other starlight wobbling. That said, if the black hole coming towards us had gas around it, gas can orbit a black hole in the same way gas can orbit a star. Like the solar system has gas in orbit around the sun. It happens. But the gas orbiting a black hole can get a lot closer to the black hole than it can the sun. And so it'll get really, really hot closer it gets. And really, really hot gas emits radiation. Like in the Cygnus X1 case, it has gas in orbit really, really close to the black hole. And that gas is really, really hot. And we're using emissions from the gas to see where that black hole is. So the deal here is if there's gas around the black hole, you can tell where it is, even though the black hole itself isn't emitting any light. So when we talk about imaging a black hole, what we're looking at is the light emitted by the gas that's orbiting it, and then a big black hole in the middle where no light's coming out of.
But another aspect of this is that we need a very certain size black hole in order to see it, because we don't have an arbitrarily large telescope. So actually, in order to see the black hole in this galaxy M87, which is 55 million light years away from us, we had to build a telescope, a virtual telescope that is the size of the entire Earth, actually, because the bigger your telescope, the finer detail you can see. And so it actually, for the wavelength we needed to see that black hole at, we actually needed a telescope the size of the Earth. And so this was a big part of the project where lots of people had to develop new instruments and new algorithms in order to make this virtual Earth-sized telescope. And actually, within our own galaxy, we know that there are lots of, as Ben said, lots of black holes of different masses. But there's actually a black hole in the center of the Milky Way galaxy called Sagittarius A Star. This is a supermassive black hole. It's about 4 million times the mass of our sun. And it shines very brightly, and we do think that there's all this gas moving around it, and that we'd be able to see it also with the Event Horizon Telescope, because it is so big. So actually, M87 is a much bigger black hole, but it's much farther away. And then the black hole in the center of our galaxy is a relatively small for supermassive black holes, but it's much closer to us. So we think that they'd appear about the same size. And so we'd be able to see them with this new instrument we've developed too. But the hard part about Sagittarius A Star, which is in the center of the Milky Way, is that because it's smaller, actually gas orbits around it much more quickly than it does around the black hole in M87. And so that means it's evolving, it's breathing over the course of just minutes. We need actually to collect data over a long period of time to make a picture. And so over the course of a night, the black hole has evolved and is moving. So we actually get we would get a blurry picture, or we'd have to reconstruct some sort of video, actually, of the black hole moving. And so taking a picture of our galaxy's black hole is much harder than taking a picture of the M87 black hole.
That's wild.
But in order to see smaller black holes, we would have to build huge, enormous telescopes much bigger than the size of our Earth. And so we don't really have any hope of seeing any of those in the near future.
That's so insane to think about.
I just wanted to stress this point in case it wasn't obvious. Black holes are literally the hardest thing of their mass to take a picture of in the universe because they're the smallest thing.
They're like bed bugs.
How are they like bed bugs?
I don't know. Aren't bed bugs famously hard to see? Guys, I'm trying to relate. I don't have a lot to add, but every once in a while I'll throw in a joke, and hopefully it lands. It did.
No, this is great.
Yeah, so if you think of everything in the universe that has the same mass as the sun, you could have something that's the mass of the sun in a different size. So a black hole that has the same mass of the sun would be literally the smallest of any of those objects. So it's the hardest thing to take a picture of that mass.
That's wild. And Katie, you said the one that's in the center of the Milky Way is called Sagittarius A Star?
Yes, that's correct. Or sometimes people call it Sag A Star for short.
I would, or SAS. Why the addition of A Star?
I think that this is just the weird history of how people name things in astronomy. So Sagittarius refers to the fact that it's in the constellation Sagittarius,
okay,
which really has nothing to do with the fact that it's in the middle of the Milky Way galaxy. It's just like, where on the sky is it?
Gotcha,
and then astronomers, being so creative, like to name things A, B, C, D, starting with whichever thing they found first. So the first thing is A, and then the second thing is B.
Oh, so it's like, okay, so it's going in alphabetical order. It's not A as in a a dog.
Oh, yeah.
Okay.
Yeah.
I see.
And I think that the star is referring to the fact that it's a radio observation, because people knew of all of these ordinary stars in Sagittarius before they started doing radio observations in the 60s.
When we say Sagittarius A Star, we don't mean STAR. The phrase corresponds to an asterisk in the name. So it's Sagittarius A asterisk. And so we say star instead of asterisk.
Okay. Yeah, because
it's not like a star like our sun.
Gotcha. Yeah, because my hang-up was thinking like Chance the Rapper, where I was like, oh, it's the name and then what it does or what it is, right?
But I think that the naming is still, it's not completely well known why you choose certain things. So, for instance, when we published the results of the black hole in M87, it was a big conversation if we'd add a star at the end. So I think it's not well defined what the star means.
And did you?
We did add a star, but you could either say the black hole in M87 or M87 star.
That's great.
It's more of what people pick up is the terminology, what the rest of the community will use.
To add confusion to this, the reason it's called M87 is because there was an astronomer named Messier who took all the photos of the puffy things that didn't look like stars. So these were galaxies, I guess. And so each of those is in a catalog called the Messier catalog and has a number. And so there's an M1, an M2, and M3, all corresponding to different lines in the catalog. So M87 corresponds to a galaxy. So it's named M87 because it's line number 87 in the Messier catalog.
There's an electronic artist named M83, and now I'm suddenly realizing that's probably what they named themselves after.
Oh, cool.
So
Nice.
so that's my biggest epiphany and takeaway from this podcast.
Okay, so let's talk about the machine itself, the Event Horizon Telescope, because it's kind of bananas. The question is, how do you take a photo of something that's really, really tiny? Black holes are absolutely minuscule. Like, the sun is an enormous ball, but if the sun turned into a black hole, it would be smaller than a city. It'd be like a couple miles across.
It would be 3 kilometers across.
3 kilometers across. That's like 2 miles. There's nothing to it. So, long story short, black holes are really, really tiny. And even if we talk about gas around them emitting light, the ring of gas around them that's emitting light is also very, very, very tiny.
Well, I agree with that completely. Although, because the black hole in M87 is so massive, 6.5 billion times the mass of our sun, actually its event horizon is about the size of our solar system, or past Pluto, the size of our solar system. So it's for as massive as it is, it's very small, but it's actually, I guess, big in the grand scheme of things.
Yeah. So, long story short, what do we do to take these photos? The first thing is you have to choose things that are big enough, even though they're really far away. But there's another aspect to this that kind of comes into basic astronomy. I got a question, Adal.
Yeah.
You know, like, good cameras, they have big lenses, right? Like, if you buy, like, a really good SLR camera with, like, a telescope zoom, it has a huge lens on it.
Yeah, exactly. Yeah, anytime you see sporting events, all the photographers that are the official professional have those long telescopic lenses.
Why aren't these lenses getting smaller? You know how, like, our iPhone cameras have teeny tiny lenses? Mm-hmm. Why do we need huge lenses still?
To compensate.
The answer is actually subtler than that, because you can't get away from getting a big lens. And the reason has to do with kind of a limitation. It has a name called the Rayleigh Criterion, or the Rayleigh Criterion, but don't worry about that. It's named after a person.
Sir Walter Rayleigh.
No, I think it's Lord Rayleigh.
It's a different Lord Rayleigh. But here's the basic idea. It has to do with, like, you know how there's lots of megapixels on our cameras, on our CCDs? The idea is the more megapixels you put in your camera, the more refined a photograph you can take, right? The more detail. There's an upper limit to that. There's a limit past which putting more pixels on our film doesn't increase the resolution. And that limit has to do with the mathematical field of optics. But the idea here is that the wider your telescope lens is, the finer resolution you can get, the more zoomed in you can get.
Okay.
The idea here is if you used an iPhone camera to take the same zoomed in photograph for your sports thing that your professional photographer did, it might be that the object is so far away that even with all the megapixels in the world, you're still going to get a blurry photograph, because you need a wider lens to be able to get that resolution into your film.
Gotcha. To take a picture of a black hole, flash? No flash?
No flash.
No, you need a backlight.
Yeah, it has to be backlit. So the deal here is that there are two limiting factors to the resolution that you can get in a photograph or in your instrument. One of them is how wide your lens is, and the other is the wavelength of your light. Do you know anything about wavelengths at all?
Not really, no.
Okay. The idea is that light has different colors, and every color can be described in terms of a wavelength. So blues are short wavelength light, and reds are long wavelength light. Does that ring any bells?
Yeah, I mean, I remember seeing some sort of diagram in a book that, as I was reading it, my eyes glossed over like a great white shark.
Essentially, that's what we're talking about. There is a relationship, a descriptor, a numerical descriptor for a kind of color. Okay. And radio waves are also a type of light. And so we can describe them in terms of a wavelength. But the idea here is that the wavelength number for radio waves is really, really big. And what that means in terms of your camera is if you had a camera that can photograph radio waves, it would need a really wide lens to be able to take high-resolution photographs.
Okay. This
is actually one of the limiting factors, because when we take a photo of these black holes, we need to take it in these radio waves, because that's the type of light that the gas around them is emitting. So the deal is that they're tiny objects that are really, really far away. And so you need a huge lens to be able to even see the detail.
Gotcha.
But when you do the calculation for how big the lens needs to be, it needs to be like the size of the Earth.
Yeah, which Katie mentioned and said you accomplished.
Yeah. Isn't that bananas?
It's going to take me like a week to digest that because, yeah, my brain is still reeling from that concept.
Honestly, you would have heard of it if we built a telescope the size of the Earth. Right?
Yeah, or I'd see it when I look out my window.
Exactly. It'd be huge. It'd be like, yeah. So what did we do instead? There's a trick in astronomy called interferometry, which means it's a measurement tool that uses interference. Have you ever seen like Contact, that movie where Jodie Foster's sitting on a car? And there's like all those radio telescopes side by side behind her? Right. So the idea is that all those telescopes side by side, they're putting their signals together in a way that makes it kind of like having a 10-mile wide telescope.
Oh, they're like a family.
Yes.
They're helping each other out. That's like an improv. It's a team sport. It's a group effort.
Yeah,
totally.
It is a group effort. But you know how in improv, the different people have to yes-and each other?
I've heard of the concept.
Yeah.
I don't practice it, but I've heard of it.
Oh, I see. Okay.
You've clearly never listened to Hello from the Magic Tavern.
The idea is that we can combine the signals from all these different stations, all these different smaller telescopes. You can combine them together to effectively make a really, really wide telescope. But doing it is kind of tricky because you need all of the telescope signals to combine in a really specific way.
So one analogy that my friend Michael Johnson, who is also on the Event Horizon Telescope project, uses a lot, and I think it might help to explain the idea of interferometry, is he says, okay, think about it like you are in a pond and there's a bunch of ducks in the center of the pond and they're kind of flapping around, moving their feet and causing ripples in the pond. And you don't know where the ducks are. So let's just say you see there's just one duck flapping around and you sit on the shore and you see the waves as they come to you. And you see they come up and down and up and down. You might not be able to, on your own, figure out where the duck is. But if you get a bunch of friends and you put them along the shore at different locations, then you can actually triangulate where the duck is coming from. And if you have multiple ducks kind of flopping around and you record the times that the waves are coming up and down and you compare them to the notes of your friends of when the waves are coming up and down, you can try to figure out where the ducks are in the middle of the pond. And so basically, we can't build a telescope the size of the Earth, but by having different telescopes distributed across the globe and that they're all watching the waves of light coming from the black hole and recording it, we can bring them back to a common location, compare the waveforms at each point and figure out, oh, where is the light coming from? What is the structure of the light? Just like those ducks. So that's kind of how I think on a high level, it kind of works.
I love that analogy. And also, my brain is a terrible thing. And immediately when you mentioned the analogy, I started to think of quack hole. It's not fun or enjoyable to say.
No, I enjoyed it. That was great.
My brain did, and I apologize for my brain in advance.
So, Adal, I have a question. What do you picture in your mind when you think of a radio telescope?
Oh, boy. I don't even know. I mean, I don't know if I've seen one before.
Have you seen the giant bowl-shaped dish in GoldenEye?
I've seen it, and in the N64 game, I played it.
Yeah, so that's a giant radio telescope.
Oh, okay.
So radio waves are coming down from space and hitting every little patch of that giant bowl and then bouncing back up to a receiver. And that receiver can be in different places. But the idea is that this dish is designed in such a way so that the radio waves bounce off of it and add together when they get to the receiver. And that's called constructive interference, where they add together in the right way. So actually, this giant dish would work if you just took big chunks out of it. You don't need the entire bowl there. You could actually get away with just, little chunks of the dish. And it would still kind of act the same. You would just get a weaker signal. But what's important is just that the time differences between the radio waves that are hitting different parts of it are the right time differences.
Yeah, the bowl is shaped in a really, really specific way so that, let's say our telescope is focused at one specific point in the sky. It's made so that the light from that one point is going to bounce off the dish and then come together at a point in a way that amplifies the signal. But if there's another point of the star, maybe a star right next to it, that's just a little bit off center, light from that star, when it bounces off this very carefully shaped bowl, it won't get amplified. And so the bowl itself is constructed in a really, really specific way so that only the little patch you're looking at will have its signal amplified and everything else around it will be quieter.
Gotcha.
And so you can use it to focus on one little patch of the sky instead of just getting noise.
Where is the Event Horizon Telescope located?
Well, that's what it's so cool. Actually, it's not located anywhere in particular. It's all around the world. So we had telescopes in Hawaii and in Spain and in Chile and in Mexico, in Arizona, and even at the South Pole. And so in order for us to make a picture of a black hole, actually all the telescopes kind of had to swivel and look at the black hole at the exact same time. And what they do is that each telescope records the waveform. So it essentially freezes the light that it is seeing on hard drives. And this data is kind of time tagged. We have atomic clocks at each of the telescopes that says precisely what time that signal was received. And then later on, once they've all been recorded, we record petabytes of data, many, many, many hard drives that are then we ship them together and process the data at a common location. So just like if you had a big dish, right, where you're kind of just seeing pieces of the light, and then later on we combine them, like the light of a single dish telescope combines it physically, we combine it computationally. One thing that people sometimes get confused at is we don't actually take a picture at every telescope. We're only collecting the light, like a single stream of light. So it's not like we take a picture at every telescope and then combine them together. We combine the light together to make the picture.
I don't think I'll ever fully understand this, but the little I do is mind-blowing.
Okay, you know how IKEA furniture works, right? Most furniture stores have the dignity to get the parts and put it together, and then you buy it complete. IKEA, they send it to you, and then you have to put it together yourself. But you have the instructions to do so you know how each of them fits together. The idea here is that if we did have a telescope the size of the Earth, then all that light would hit all of the different parts of the bowl and then bounce back into the center and amplify itself. But instead of building it, what we do is we take a bunch of little individual telescopes and we receive their signal, and it's like the unpacked IKEA furniture. You say, if I was a huge bowl, the bowl would combine and collect all these different pieces of data together to give us this couch. So what we're going to do is, instead of building this giant bowl, we're just going to collect the information and say, hey, if it was a bowl, this is how that bowl would combine all the information. Okay. But to do it, to build that IKEA furniture, you need to know exactly when each signal was captured by each telescope.
So that's why you have the timestamp, yeah.
Yeah, so you timestamp each and every data collection point, and what that tells you is, if it were a bowl, this is what each part of the bowl would be receiving and bouncing towards the middle, and then we artificially combine them together when we get that flat pack Billy bookshelf home.
Can you do another analogy, but with ducks now?
In the case of the duck analogy, if we all put ourselves along the edge of the pond, and we all stood shoulder to shoulder, that would be like a dish the size of the Earth. But now I only have so many friends. I don't have many friends. And so my few friends stand along the edges of the pond, and we don't see the waveform at every location as it hits the shore.
But we still have enough
but at some locations. And so we try to combine that information.
That's wonderful.
Yeah. And I also think we missed one thing that I think might help. Although you probably get the idea the black hole is really, really small. But just to explain how small it is, it's about the same size as if you held an atom at arm's length. So that is what we're trying to see, something that's that small, one atom, an arm's length away from you. Or an orange on the surface of the moon. Or what's another one they do? Like, I've heard something about like reading a newspaper in LA from New York. It's like that. Yeah, so it's very small.
Absolutely insane. So I'm grasping the size. I'm grasping hopefully a lot of it. It's unbelievable that we have this picture now. What's next in terms of, Katie? Are you working to get a clearer picture? Are you working to get pictures of other black holes? Like what's the focus, if you can speak to it?
Yeah, we just kind of at the beginning, basically we were working on building an instrument that we, had never used before, looking at something we had no idea what it was going to look like. I mean, we had some predictions, but we didn't know what was going to happen. And so it's kind of just amazing that we've been able to show that, we got something that theorists had thought for years, that this might be what it looks like. And so I think that's kind of amazing that we saw something that was so amazingly consistent with the predictions. And so, and from this image, we can start studying not just about general relativity, but also about the immediate environment around a black hole, how black holes, how matter accretes onto them, how they impact their host galaxy. But it's really, I think, kind of just the beginning. Now that we know we have this extreme laboratory of gravity, we can continue to test these things, and we can try to improve our instrument and our algorithms in order to, learn more about the black holes that we think we can see from it. So this is really just the beginning. There's a lot of stuff, even with the data that we made this image from, that we can do. So this is a total intensity image. We're just looking at the intensity of the light, but actually light is a vector. It has a polarization, and we collect the polarization of the light too. And if we can make an image of the polarization, the direction of the light, we can learn things about the magnetic fields around black holes. And also, I talked about the black hole in the center of our Milky Way galaxy, Sagittarius A Star, and that one is evolving on the timescale of minutes. You would expect gas to rotate around it every 4 to 30 minutes. So over the course of a night, when we observe the black hole, we might see a lot of evolution, and we can learn more about the space-time around a black hole and how gas orbits it and the dynamics of it. And so these are things that we can now go back and study now that we know it's possible. And we're definitely working on that, in addition to thinking of how to improve our instrument in the future by either adding more dishes to the array. We only have a very small number of dishes that we use so far. It's like a sieve which it was a very sparse array of dishes. So if you add more, we can get a clearer picture. And even adding dishes to space, we're thinking about, having satellites orbiting the Earth that would give us a way to make movies of the black hole over time.
That's exciting.
So these are things that we're doing now. But actually, a big reason of how we're improving our instrument, and a lot of people are working on how can we improve it, is because of the fact that we work with such small number of dishes, and also the data that we collect from every dish is really noisy for a number of reasons, but partly because the atmosphere above every dish kind of corrupts the signal that we get. And so we get this really sparse and noisy data. And so actually making a picture from it is very difficult. And so if we can try to improve it by adding more dishes to the array, then hopefully we can get better pictures and learn even more.
That's very exciting.
I think we should speak to that particular detail a little bit more, because it's honestly kind of bonkers. Like, so far, our explanation of how we're artificially taking the signals that each of these telescopes is and combining them in a computer to essentially make an artificial telescope the size of the Earth. I mean, that makes sense, but the devil's in the details when it comes to putting that information together. Have you ever woken up at maybe 5 a.m. because you have to go catch a plane or something, and the lights are all out in your house, and you can just barely see anything because it's super, super dark, and you see a shape, and you're like, is that a lamp? Or is that my dog? Or you can't quite figure out what you're looking at because there's not enough light. That's almost the threshold. Because having a dozen telescopes around the world, the width of the Earth increases the resolution, but it doesn't have the collecting power that a telescope that big, that a lens that big would have. So it's still pretty dim. And also, like Katie said, the data comes in kind of crummy. The real tour de force here is in taking those petabytes. How big is a petabyte? What is it? 1,000 terabytes. Oh, so many zeros, right? That much data, and collecting it and refining it and turning it into these images. That's a bonkers. I don't even know how to start. Whoa. How? So essentially, they took all these computers, but it's still very, very, very dim. How do you take your computers and this noisy information and refine this pretty great image, this high-resolution image out of it? So yeah, I think that's worth talking about.
Absolutely. That's wild.
It's wild.
So actually, from the measurements that we get from the small number of telescopes, we can get some information about the structure of the black hole. And so it actually turns out that for every 2 telescopes we get something about the spatial structure of the image. So the closer 2 telescopes are together, we get information about broad structures, so large-scale structures. And to get the high-resolution information we need to see the ring, we have to put our telescopes really far apart. And so it's very much like hearing notes in a song. So for 2 telescopes that are together, we hear low notes of the song, and then telescopes that are very far apart, we hear high notes of the song. But we only hear a few notes of the song. And so because we only have a small number of notes, trying to figure out what the song is that's being played on a broken piano, basically. Yeah. And so if you have a broken piano, there could be an infinite number of songs that are perfectly consistent with the notes that are being played, right? The other notes you could just be banging on them randomly, right? But if you hear a song with only a few keys that are missing, you can probably still figure out what the song is that's being played.
And it's probably chopsticks or heart and soul.
Yeah, right. Well, yeah, hopefully those keys are not broken for chopsticks. But if you have too many keys that are broken, you might not be able to figure it out. So it's this hard problem. So from the data that we collect from the telescopes, we get basically only a sparse number of notes that we're hearing. And those notes are even jumbled. They might have been played at the wrong time, even. And the goal of the imaging process, how we had to make an image, is we had to find what image would be consistent with those notes. So find the song that is consistent with those notes. But to do that, we had to also think about, what is a likely image? What is a reasonable image? Just like you wouldn't expect if someone is playing Beethoven, right? You have some idea of,
Can we use Bach, for example, instead of Beethoven, just so it's a Bach hole?
Sure. That's great. I love that. So yeah, we're playing Bach, right? Maybe we don't know all of the songs, but we know it should be pretty.
Yeah. So you kind of know what Bach sounds like, right?
Yeah.
Yeah, you kind of know roughly what Bach sounds like, and you wouldn't expect the other notes that they should just be you just banging on.
Yeah,
them.
it's not going to be John Cage or Philip Glass or something, because those sound different than Bach sounds.
The idea is then we have to find an image that is consistent with the sparse and noisy measurements we take, but also is reasonable. The hard part about that is that we have to define what is a reasonable image. And that is a hard problem. For instance, we don't want to tell our algorithms that a reasonable image is something that looks like a ring, and then we're happy that we recovered a ring back in the end, right? We don't want to tell it something about what we're testing. We want it to be as agnostic as possible. So a big question we faced in dealing with the data from the Event Horizon Telescope is not just how do we make an image, but how do we actually verify what we're reconstructing is real? We wanted to really make sure that we weren't telling it what it should look like. We wanted to give it a lot of space to explore all possible explanations of images, but we had to still remove ones that are completely outrageous.
Of course.
For instance, like if you had unplugged the cable on your television and just saw white noise, we wouldn't expect it to look like something like that. We'd expect the light to be positive and for it to be somewhat compact and things like this. But even then, we wanted to spend a lot of time in verifying what we were reconstructing was real. And that was actually a huge part of the process in getting the image, was just testing the image.
Wow.
So Katie, I think I remember hearing once that you did like image reconstruction tests or like competitions with the different algorithms. What were the weird images that you guys fed into your pipelines to reconstruct?
Yeah, so even before we collected data, we collected data in April of 2017, and for years before that, we were developing the imaging methods, and we actually wanted to test ourselves before getting the real data. So we set up a bunch of challenges. We called them the Event Horizon Telescope Imaging Challenges, and there we made synthetic data that was, if you knew what the true image was on the sky, what kind of measurements will we expect to see with all the different kinds of crazy noise that we expected from the telescope, all the problems that we face with the telescope. And the point of these challenges was that a group of people would generate synthetic data, and then we would pass it off to people who would use their algorithms to try to reconstruct an image from it. And we tested ourselves on lots of different things that we thought black holes looked like, but also crazy things. For instance, we used at one point a snowman, and we didn't tell anybody what the pictures looked like. So a lot of people, for instance, some people thought it was like a binary black hole that we were getting back in the end, but it was actually just a snowman. And so we tested crazy images that we wouldn't expect and made sure that our algorithms were able to recover the general structure of the true source image and not just trying to get back rings in the end.
Was everybody able to recover the snowman?
Yeah, I mean, because every algorithm, you have to inject some sort of information about what images look like, and also different humans tune knobs on their algorithms differently. Every image looks different, but all of them actually recovered the general shape of the snowman. And so that's quite important that we do something like this, because it gives us confidence that we would be able to recover an image that was surprising in the real data. We weren't just recovering rings. But one thing that was also really important is, as I said, every image looks different, right? Based upon its underlying assumptions of what you say is a likely image. And so by comparing across the methods of the images that were done by different people and different methods, we could build up confidence in certain features and then say, oh, no, that feature that's only appearing in one of those images is probably just an artifact. So this kind of informed actually how we were going to approach the real data from the Event Horizon Telescope when we got the data from the M87 black hole.
Does this crazy process kind of make sense to you? The idea that, like, okay, so you get this data, and it's like, even after you do all of the fancy cleaning up of the data using fancy statistical methods and combining the different telescopes in different ways to make the data a lot cleaner, you still kind of don't have enough to quite make it out. And then so you have to kind of make your computer guess what it's looking at. Mm-hmm. And then so what she did, you were supervising the teams, weren't you, Katie?
Oh, there was a number of people who were really integral to making the images. There was different levels of team structures, of different leaders, of different parts of the project.
Katie, as far as I'm concerned, you did this.
No, I didn't. I really didn't. This was a big, big team effort.
They split them up into a bunch of different groups where the groups weren't talking to each other, and each group had to come up with its own kind of computer intelligence that would take the raw data and guess what shape they were looking at. So to test this, for instance, they'd make a bunch of fake data. They'd take a computer image of like a snowman, and then they'd say, okay, if the telescope was looking at the snowman, here's what the crummy data would look like. And then they made the computer software of each different group interpret that, and each of them saw kind of a different shaped snowman-ish.
The same shaped snowman, but different. Each one looks different still.
So because each of these groups were using a different homemade algorithm, you could kind of compare and contrast the different groups to get more information of what they're looking at. So you'd say, well, they didn't know that it was a snowman shape, but all of these different groups are kind of getting the snowman shape. So the original image probably had the snowman shape.
But because we have such little amount of data, sometimes the algorithms make spurious features. You'll get a little wisp of light at one point, but that might not appear in all of the images because that's very dependent on the exact algorithm that was used to make the picture. And so by comparing across the images, you can kind of see, these are common features that are appearing no matter what algorithm or person made the image.
Carrot nose, stovetop pipe, yeah.
Yeah. But some random features around it, you might say, that doesn't look like it's real because it only appeared in one of the reconstructions. And so this gave us a way to look at and assess common features among independent reconstructions. And so when we approached the M87 data, we thought that this was really important, and we wanted to avoid some sort of shared human bias like we had done in these challenges. So what I mean by that is because these algorithms are sensitive and sometimes you have to tune your knobs to get them to work. If I saw my friend made a beautiful picture of the data from the M87 black hole and I say, oh my gosh, that's a beautiful picture, I might subconsciously make my algorithm produce an image that looks similar because there's so many degrees of freedom. And so we wanted to prevent this from happening.
Cross-pollination sort of unintended influence.
Exactly. So what we did is we split up our big effort of about 40 different people who either develop imaging methods or they're knowledgeable users of imaging methods. They have a lot of experience in it. Into 4 different groups, actually. And 2 of these groups kind of worked on more recent methods that have been developed in the last couple of years. And then 2 of them worked more on traditional methods used in radio interferometry and radio astronomy. And basically, we told the teams, okay, we released the data to them, and we said, okay, go off in your separate rooms and don't talk to each other from the other teams for 7 weeks. And we gave people 7 weeks to come up with their best image. And within our team, it was quite amazing. We made this image, but we were still, maybe we're having this human bias. Maybe we're pushing the image in one direction. So actually, what was the most amazing part of the process is that after 7 weeks, we all got together and we showed our best images from every team on the screen at the exact same time. And we saw that although every image looked different, just like in the snowman example, they all looked different. They were all done by different methods with different underlying assumptions, and different people ran them. They all contain the same ring-like structure of about the same size, a 40 microarcsecond ring that was brighter on the bottom than the top. And so that was kind of, for me, the happiest moment I've had in this collaboration because, when I made an image, I had no idea. Was I biasing it too much? Was I pushing it too much in one direction? But when I saw no matter the person, no matter the algorithm who had taken this data, they got a same basic structure back in the end.
Yeah.
That brought a different level of confidence to our results. So that
to know it to be more likely to be true, that's wonderful.
Yeah. So I think that was a really essential part of the process, that we had so many people who developed many different algorithms and worked together to build our confidence in this result.
Was there and I'm going off of Apollo 13 or movies like that, was there a moment where you took a stack of papers and threw it in the air to celebrate, or like a fist bump?
We didn't have that, but I was so nervous. So we all gathered at the Black Hole Initiative building in Cambridge, Massachusetts. And I remember I was supposed to click the button to reveal all the images at the same time. And I was just so nervous. I didn't want to do it because I don't know. We could have gotten anything from the other teams. And I wanted it to be so so real. But seeing those images come on the screen.
Yeah, what a cool
It was
moment.
exciting. And we have a picture from it. We didn't have anybody film it because we were very sensitive about leaking data, but we have a picture and you can just see everyone is just so, it was an amazing time for us. We were so excited.
That had to have been very emotional and very overwhelming.
Did you have like some champagne or some cake to celebrate?
We did actually. So we had champagne later that night. It was a fun time. And we all went out for beers and sang Black Hole Sun actually in karaoke. But we changed it to Black Hole Shadow.
Yes. Honestly, every time I hear that song now, I'm going to just, wherever I'm at, I'm going to be like, it should be Shadow. And then I'm gonna launch into why.
That's my ultimate goal. But even then, actually, even after we had gotten these 4 pictures from the 4 teams that looked very similar, we still were afraid that maybe this could still be some result of human bias. Remember, I said we all have those knobs.
Yeah,
and we all kind of, we thought that it could be a ring, right? So maybe we all are still pushing it in a certain direction. The algorithm's
trying
in a
to
certain
manipulate
direction.
to make it produce that, absolutely.
Yeah, so we really wanted to be very sure with these results. So actually, we took the next couple of months to basically try to break our methods, to try to make sure that if we remove humans from the loop as much as possible, that we still get that ring back in the end. So to do that, we tried to remove humans by, instead of humans choosing those knobs, we had computers try to choose those knobs by training how to tune the knobs to get other sources, structures back. So for instance, we created synthetic data from something like a disk that has no hole in the center. And we created synthetic data as if the Event Horizon Telescope were actually seeing a disk on the sky. And then we said, okay, let's tune the parameters of our imaging method to try to recover that disk shape back as well as possible.
Yeah.
To make it so it doesn't have a hole in the center. And then we would transfer those parameters onto the actual data from the M87 black hole. And we found that our algorithm still required us to put a hole in the center.
Wow.
And so we did this with lots of different kinds of training, testing procedures on many different kinds of underlying sources and many different imaging code bases. And we found no matter what, we basically needed to make a ring shape.
Yeah.
And so that was, the second level of confidence that we had basically in our images.
Were you able to tell family? Were you able to tell or did you sign like an NDA or what's the protocol?
So we actually made the first images in the summer and we had to keep our lips shut. I might have leaked it to my husband, but but my family, like my parents and my siblings, I didn't tell them. We didn't tell anybody. So it was fun to finally be able to tell people what we've been working on.
Can I ask something?
Yeah.
So I'm so sorry. What was the name for the black hole?
M87 is the name of the galaxy. Yep.
Okay. Did you have, while working on it, was there any sort of inter-office
code
nickname for it? Was there a code name or nickname for it?
No, actually.
We should have. Little hole or something?
I can't.
Big hole.
No. But we did, if people accidentally saw it, which I don't think happened, at least with my friends, but we would always be like, oh, that's just a simulation. Just a simulation. So actually, we were very surprised that people in our office, we thought everyone would know, but everyone said they were very surprised, actually, and they didn't know. So I was surprised at that we were so good about not leaking it.
That's fantastic.
One thing I do want to mention about the data processing, actually, is so I mentioned that we take these petabytes of data, but actually, when we start the imaging, when we try to make the black hole image, we don't take in petabytes of data and then make it, an image pops out at the end. There's this whole other stage of data calibration whose goal is to take those petabytes of data and reduce them down into basically the megabytes of data that we use for processing. And so basically what happens is that you record hundreds of terabytes of data at each telescope, and then it's so much data we can't even send it over the internet. And so it actually has to be flown in airplanes to a common location. And then at that common location, we actually have a special purpose supercomputer called a correlator that combines that data using that precise timing from the atomic clocks I talked about. And then from that, there's also the stage of calibration where we reduce it even further, try to beat down the noise and get that tiny little signal that's riding on a huge amount of noise out of the data. And so this was also a big part of what needed to be developed for the project as in terms of data processing. Developing this calibration pipeline had to be developed in a very unique way for the Event Horizon Telescope data, and it was a big endeavor in itself. People kind of forget about this data processing because it's not glamorous. Produce an image at the end, but it was really, it's not as glamorous, but it's just as important to getting that image.
It's so funny to think about something is so big as it can't be processed by the internet, so you have to fly it to a supercomputer. It's so funny to me of like...
Yeah. Actually, the data... So I mentioned we take data at the South Pole. Although that data isn't actually used for the M87 black hole, it's used for other sources we look at. And because actually we record the data at the South Pole during their winter time, and there is no airplanes that go out or in from the South Pole during the winter. So we actually have to wait for their winter to be over in order to get the data.
Wow.
So we got the data we took the data in April and we got the data in December. And if you were trying to send it over the South Pole internet, it'd be something like, I think someone calculated 25 years to transfer that data. So yeah, it's better just to wait for the airplanes to fly.
Yeah, of course.
Well, that was fantastic. Thank you, Katie. Thank you, Leo. You've pleased me. Your efforts have borne fruit, and that fruit is very, very sweet. Here is some fruit. Dr. Katie Bouman, you get a plum.
Oh, yay. Yum, yum.
And Dr. Leo Stein, you get a Japanese persimmon.
Ooh, yum, 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 yum.
I'd like to thank my guest, Adal Rifai, from From the Magic Tavern and his new podcast, Hey Riddle Riddle. For links to his podcast, you can Google it or visit our website in the show notes. Thank you very much.
All I got was a celery.
What? No, you got the fruit of knowledge this whole time.
Celery? Oh, an apple.
Well, that was absolutely fantastic. Don't forget that you can listen on past the final music and hear some excerpts from our conversations. Some stuff I cut out because it was interrupting the flow. You know, most of our episodes have little snippets of conversation after the last bit, right? Anyway, it's time for the announcements. So there are some pretty fun ones, so please pay attention. Now, first, the hiatus is over. Congratulations. We're now in a phase of the show I call the March to 100. I'm going to try to have monthly episodes from here on out. We'll see. But I've got a little bit of a buffer now, so here is hoping. Number 2, we're going to have a live show this coming February at the AAAS 2020 General Meeting in Seattle. That's a conference of the AAAS. I guess they regularly have a day or two of live podcasts. So we're going to participate this coming year. So if you want to come to this conference, you can hear us do a live show. Third, we now live in the promised era where podcasts are finally going mainstream. There are so many great shows out there. Even Conan O'Brien has a podcast. It's fantastic. But it's important when your mom or brother-in-law starts listening to podcasts that they know there's more out there than just shows about celebrities or shows about true crime. In fact, there's a show for every interest, even if your interest is in black holes and neutrinos, which means I'd like you to spread the word, about us, hopefully. Review us on the iTunes or the iPhone podcasting app, or talk about us on social media. We've got a Twitter page and a Facebook page. In addition to that, we're on Stitcher, Google Play Music, Spotify. I think we're on Pandora, and we're even on YouTube. Any way you want to listen to us, you can, so please dock us up. Fourth announcement. I've decided to start doing a thing where if I can't find a cool guest or our planned guest cancels at the last minute, I'll choose a listener for the show to come and sit in the guest chair and chat with us about physics. The way I do it is I put the call out on Twitter or Facebook. So to be a guest, you need 3 things. The first is to follow us on Twitter or Facebook. Secondly, you'll have to have a fast internet connection and a quiet room in your home or workplace where you can use this internet connection. And the third is that you need to be available when we want to record. That's it. So if you follow us on social media and you want to be on the show, you might get lucky. Finally, we're still humbly soliciting your donations. Your donations go for paying our server fees and our episode transcription project, and buying our physicist microphones, and paying our travel costs to that live show. So, if you'd like to help support us, you can send one-time donations through PayPal off of our website, or you can go to our sweet Patreon site and give a recurring $2 or $5 donation. If you give more than $2 and supply your address, I'll send you a postcard with a bunny on it. This particular episode of the Titanium Physicists has been sponsored by a collection of generous people. Firstly, I'd like to thank the generosity of PK and Amir Ayal. I'd also like to thank Aaron Wheeler, Sander Boros, a badger, the septet Baylor Fane, and Luke Edwards, a Mr. Astro Yuki, Shivang Patel, Mr. Martin Myulka, Henry Rabon, Peter Scott, Russ Mutsi, Ayush Singh, and Matthew Sullivan, a Daniel Lauzon, Patrick Eon, Kevin Forsyth, Yer Panay, Huainam Duong, Stian Herrickson, a TPR Jones, Pascal, a man named Ryan R., and Michael Usher, Senor Canada, Adrian Schoenig, Sarah Stradler, Louise Pantanella, a guy named Ben, a Mr. Matthew Lambert, a fellow named Ayush Singh, a David Myrtle, a Mr. Ryan Foster, a Janica Freifenberg, Steve Smethurst, Magnus Christensen, Bart Gladys, and Mr. Stuart Pollock, our Emperor Courtney Brooke Davis, Mr. David Lindels, Mr. Carl Lockhart, our eternal friend B.S., and Randy Dalzell, a Ms. Tina Raudio, the enigmatic Ryan, a gentleman named Crux, and Gabe, and Evan Weens, David D., and Dan Vale, a Mr. Alex, WTL, Mr. Per Proden, Andrew Waddington, Mr. Jordan Young, John Bleasy, a Brittany Crooks, James Crawford, Mr. Mark Simon, Tucson's Gang of Wind, Mr. Loris Lee, Sixton Linnison, Mr. Simon, Keegan Eade, Andreas from Knoxville, Cadby, Mr. Joe Campbell, Alexandra Zani is great, Winna Brett, Eric Dutch, Etienne, and a gentleman named Peter Fan, Gareth Eason, Joe Piston, David Johnson, and Anthony Leon, as well as Doug B., Julia, Noah Robertson, Ian and Stu, a Mr. Frank, Philip from Austria, and Noisy Mom, Mr. Shlomo Dalal, Melissa Burke, Yassine Urazazi, Spider Rogue, Insanity Orbits, Ryan Johnson, Madame Sandra Johnson, Mr. Jacob Wick, Mr. John Keys, a Mr. Victor C., Ryan Kloss, Peter Clipsham, Mr. Robert Halpin, Elizabeth Teresa, and Paul Carr, a Mr. Ryan Newell, Mr. Adam K., Thomas Shire, Mr. Jacob S., a gentleman named Brett Evans, a lady named Jill, a gentleman named Greg, thanks Steve, Mr. James Clausen, Mr. Devin North, a gentleman named Scott, Ed Lowlington, Kelly Wienersmith, Jocelyn Reed, a Mr. S. Hatcher, Mr. Rob Abrazado, and Mr. Robert Stietka. So that's it for Ti-Fi this time. Remember that if you like listening to scientists talk about science in their own word, there are lots of lovely other shows on the Brachionote Media Network. If you're wondering which show to listen to, try Science Sort of. It's our old favorite. The intro song to our show is Tell Balgary Balgary's Dead by Ted Leo and the Pharmacists, and the end song is Russia by Ramona Falls. Good day, my friends, and until next time, remember to keep science in your hearts.
I visited Russia. I started folding until in one precious doll I had poured in all of Siberia, and I said, love, here ya go. She said, too little too late. Trip to the Nile, where I started swimming upstream till Ivano, where you found the spring bloom with God's purest water from above the Father to heal her. She said, too little too late.
What is, in terms of like the power of it to destroy, is there ever a fear in our lifetime or in the near future, I guess, relatively, of like a black hole able to suck in Earth at all? Like, is that ever a thing that could happen? Because I know, again, in movies and sci-fi, there's, planets and spaceships being sucked into black holes. Is that a thing?
Not really.
Well, there's nothing that says that it couldn't happen, but, we would just have to get pretty unlucky. Black holes are, not every type of star makes a black hole. Only the really heavy stars make black holes. So most of the stars in the universe are just gonna, stop burning and then make little dim things, but they're not going to turn into black holes.
Yeah, so it's like Tom Cruise versus Mickey Rourke. Mickey Rourke just kind of fades away.
Yeah, so how many Mickey Rourkes are there for every Tom Cruise, right?
Wait, no, black holes are Tom Cruise in this explanation. And Mickey Rourkes are like the red dwarfs.
So Tom Cruise might come along and jump on your table, but it's much more likely that you'll run into Mickey Rourke or, one of the many thousands of Mickey Rourke-like people out there instead of Tom Cruise.
Yeah. Exactly. The last time, and this is a true story, the last time I went to L.A., I went to a restaurant hoping to run into John Hamm, and I ran into Pauly Shore. So
wow, that's some special luck you got.
Yeah, I know. So there's a lot of Pauly Shores around. It's very unlikely to meet John Hamm.
I don't think we have any fear of being sucked into a black hole anytime at least in our lifetimes.
Good. That's the only reason I came on this podcast, is for my own safety, to assuage the fears of my family and friends.
Yeah, there's lots and lots and lots and lots and lots and lots of space between every star. Stars rarely hit each other. Stars rarely pass really close to each other unless they were born together. So the likelihood of the solar system getting disrupted by a black hole is very, very small. Don't worry about that.
Katie, do you become, when you're out in the world, do you become massively frustrated because you're so incredibly intelligent, do you just become frustrated with everyone around you?
No, of course not. No, but actually, I'm not a physicist.
You're a level of intelligent where it's just at some point you must just get very frustrated with everyone, just the mundane idiocies of everyone around you.
No, absolutely not. I mean, I love trying to explain concepts to people who are not physicists. I'm actually not a physicist myself. I studied computer vision, basically area of computer science. And so when I started on the project, the Event Horizon Telescope project, I didn't know anything about black holes at all. And so I learned a lot by talking to people. And so I find it very helpful to try to come up with analogies and everything to explain the project. So I hope this is fun for all of us. I think this is great to try to explain it.
Yeah, I'm having fun. I was just joking in terms of you're just it's just very fun and interesting to be surrounded by very intelligent people right now.
You included me in that.
Woof. So real quick, am I the only one who didn't go to MIT?
I didn't go to MIT.
I went to Phoenix Online, so that's comparable.
Well, that's pretty cool. That's a legendary bird. It's a legendary school.
Yeah, that arises. Also, I feel a little ambushed in terms of, Ben, you said we would be discussing the movie Event Horizon. I feel a little taken aback, but I'm willing to go along with this.
We will refer to the movie as often as we can just to keep you in the conversation, Adal.
Thank you.
All right. So, black holes, what are they?